When you look up at the night sky, you're doing something very simple and very strange at the same time. You're looking back in time. Light takes time to travel, so the stars you see are showing you how they looked not just a little while ago, but often years, centuries, or millennia in the past. Turn that up to the cosmic scale, and every direction you look is a window to a different era of the past. That's the starting point for understanding what people mean by the observable universe. Before we dive in, I'd really appreciate it if you could like this video and subscribe, especially if you find these explorations useful, inspiring, or simply interesting. And whenever you'd like, feel free to drop a comment letting me know where you're tuning in from and what time it is there. It's always great to see how many different places and people come together here, all connected by the same conversation. Think of the observable universe as a bubble centered on you. It's not a physical wall or a border. It's a limit set by the finite speed of light and the finite age of the cosmos. The universe is about 13.8 billion years old, so light emitted more recently than 13.8 billion years ago hasn't had time to reach us. Except that because space itself has been expanding, the furthest regions that sent us the oldest light are now much farther away than 13.8 billion light years. When cosmologists crunch the numbers, they find that the radius of that bubble, what we can, in principle, see, is about 46.5 billion light years. That number feels counterintuitive at first. How can we see objects that are now farther away than the age of the universe measured in light years? The answer is that space stretches, carrying distant points further away over time. So the light we detect now left those regions when they were much closer, and the expansion of space has moved them to the enormous distances we calculate today. Inside that bubble are everything we can study directly. Galaxies, quasars, the cosmic microwave background, clusters, and voids. Outside it, possibly more of the same or something completely different, we don't know. There are solid reasons to think the universe goes on far beyond our observable bubble, possibly infinitely. But because we can't receive light or other information from beyond that horizon, anything outside is, for now, a matter of inference and math more than direct observation. One of the first puzzles that pushed cosmologists to imagine something beyond the simple expanding universe was the remarkable uniformity of the sky's oldest light, the cosmic microwave background, or CMB. The CMB is a faint glow that fills the sky, a relic of a time about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that, photons bounced around in a hot, opaque plasma. Afterward, the universe became transparent, and those photons have been traveling ever since, stretched into microwaves by the expansion of space. When instruments like the COBE, WMAP, and then the Planck satellite measured that light, they found its temperature was the same to 1 part in 100,000 across the entire sky. That's an extraordinary level of uniformity. Why is that view puzzling? Because if you trace the history of the universe backward using only ordinary expansion, parts of the sky separated by large angles today were so far apart at early times that a light signal couldn't have passed between them to even out temperatures. It's like saying 2 rooms in a house have the exact same temperature, but there was never time for the air between them to mix. Something else must have happened to make those regions share the same conditions. Enter inflation. Inflation is the idea that, a tiny fraction of a second after the Big Bang, somewhere around 10⁻36 to 10⁻32 seconds, space underwent a stupendously rapid expansion. If you imagine the universe as a loaf of raisin bread, inflation would be like that loaf rapidly puffing up so that raisins that were once millimeters apart end up kilometers apart. In practical terms, inflation stretches tiny regions that were once close enough to interact into vast swathes of space. That makes the uniformity of the CMB plausible. Before inflation, those regions could have been in causal contact and shared temperature and density. Inflation then spread that condition across enormous distances. Inflation also explains another neat coincidence. The universe appears to be geometrically flat, meaning parallel lines stay parallel, and the large-scale geometry follows the rules of Euclidean geometry to high precision. Different possible geometries arise depending on the overall density of matter and energy in the universe. Without inflation, you wouldn't expect the density to be tuned so closely to the critical value that gives flat space. Inflation naturally drives the geometry toward flatness, just as blowing up a small patch of a sphere makes it look locally flatter. But inflation does one more interesting thing. In the same way that a tiny crack in a plaster wall can be magnified into a feature, you can see across the room if the wall is stretched. Minute quantum fluctuations in the energy field driving inflation get stretched into real density variations. Those amplified wrinkles turned into the seeds of galaxies, clusters, and cosmic structure. The 1 part 10 minus 100,000 variations seen in the CMB correspond precisely to the size and pattern of fluctuations you'd expect if quantum jitter was blown up by inflation. That's why inflation is such a powerful idea. It solves several deep problems at once and makes predictions that match observations. Now, when people talk about the edge of the universe, they often mean different things. If you mean the edge of the observable universe, the furthest light that has had time to reach us, that's well-defined and calculable. But it's not a boundary in the everyday sense. There's no wall you could bump into. Space could go on forever. The edge is a limit of sight and causal contact, not a physical rim. A helpful image is standing in a fog. The fog doesn't end at a cliff, it just blocks your view beyond a certain distance. That distance changes with conditions. If the fog thins or thickens, your horizon moves. Adding one more layer of complication, the expansion of the universe is accelerating. In the late 1990s, astronomers observing distant exploding stars called Type Ia supernovae found that those supernovae were dimmer than expected if the expansion were slowing down or constant. That observation, confirmed and refined by many subsequent surveys, indicates that some mysterious dark energy is pushing space apart more strongly as time goes on. Current estimates attribute about 68% of the universe's energy to dark energy, about 27% to dark matter, an invisible form of mass that we only detect through gravity, and about 5% to ordinary matter. If the acceleration continues, in the far future distant galaxies will recede so fast that they'll slip beyond our cosmic horizon, and we won't be able to see them anymore. Our observable bubble will shrink in terms of accessible neighbors, leaving a lonely island of the local group of galaxies, and eventually, only the remnants of our galaxy and its stars. All of those are natural, physics-based ways to think about limits and horizons. But then there's a different kind of edge people mean when they invoke the idea of a cosmic illusion. Could everything we experience, the sky, the galaxies, even the laws of physics we rely on, be something like a simulation? The simulation hypothesis has become a popular thought experiment, and it was given a rigorous philosophical framing by philosopher Nick Bostrom in 2003. His argument is simple in structure. If technologically mature civilizations can create simulations of their ancestors, and if they create many such simulations, then the number of simulated minds could vastly exceed the number of original biological minds. If that's true, statistically you would expect to be in a simulation rather than the one original substrate. Bostrom presents it more cautiously as a trilemma. Either almost all civilizations go extinct before they can simulate ancestors, or advanced civilizations are uninterested in running those simulations, or we are almost certainly in a simulation. The argument is fascinating because it's mostly probabilistic and depends on assumptions about future technology and behavior. It doesn't claim to prove we are simulated. It points out a conditional probability based on a set of premises. For many people, the idea is attractive because it connects to familiar experiences. We already create virtual realities, complex simulations, and digital worlds. Video games and animated films are primitive early analogs of what a future simulation might look like. It's not hard to imagine, in the abstract, a civilization so advanced that their computers can model entire universes, or at least to the extent needed to simulate conscious observers. But the gap between imagining a simulation and proving, or even testing, whether we're in one is enormous. One immediate objection is computational cost. The raw amount of information required to simulate a whole universe at the microphysical level is staggeringly large. But a practical simulation might not need to represent everything at every point in space at full fidelity. Think about a video game. You don't render trees and NPCs in full detail until the player is nearby. A simulated universe could use clever tricks to avoid wasting resources, only calculate what observers interact with, or rely on compressed descriptions that are computationally easier to update. If the simulation is meant to be indistinguishable from reality for its inhabitants, the designers could economize in ways that make the project feasible. There are also metaphysical questions about what consciousness is and whether it can be instantiated in a substrate other than biological brain tissue. If consciousness depends on particular physical processes, then simulating the right computational structure might produce conscious experience. If consciousness requires something more than computation, simulation might not create real minds. That's a deep problem with no consensus in philosophy or neuroscience, and it makes the simulation idea slippery. Some versions of it are compatible with current science, while others step into more speculative territory. Could evidence for a simulation be hiding in plain sight, maybe in the structure of the cosmos itself? Some people have proposed looking for telltale digital artifacts, a grid or pixelation at the smallest scales, unexpected limits in energy or information transfer, or anomalies in cosmic background radiation that look like artifacts of a rendering algorithm. A few researchers have suggested examining high-energy cosmic rays for patterns that could signal a discrete lattice underlying space, or searching the CMB for glitches that could be artificial. Those ideas are creative, but none have produced convincing results. The natural expectation in physics is that the smallest scales are governed by quantum mechanics and perhaps quantum gravity, not by clever code. What looks like a systematic anomaly needs to survive rigorous scrutiny and alternative explanations before it could be taken seriously. Another angle is to consider whether the universe shows any signs of being tuned for observation in the way a simulation might be. Our laws of physics allow for complex chemistry and long-lived stars, conditions that permit life and observers. Some people see this as evidence of fine-tuning that could point to design. Others point out that even in a multiverse scenario where many different types of universes exist, observers will only arise in the ones compatible with observers. That's a selection effect. The anthropic principle says we shouldn't be surprised to find the universe congenial to life, because if it weren't, we wouldn't be here to observe it. That's not proof of a simulation. It's a reminder that our observations are conditioned by our existence. So where does that leave us? The basic facts about the cosmos, its expansion, the CMB, the distribution of galaxies, are well explained by a combination of the Big Bang framework, inflation, and the physics of particles and gravity. These elements don't require a simulation to make sense. They're consistent with a large body of observational evidence collected over decades. But the simulation idea reframes the question in a philosophical way. Even if the physical story is accurate, could the physical story itself be running on top of something else? That's a type of question that blends science with metaphysics. One practical way to think about the simulation hypothesis is to ask whether it makes testable predictions. Science advances by proposing models that can be falsified or confirmed by experiment. If the simulation idea makes predictions that differ from standard physics, and those predictions are experimentally accessible, then the hypothesis steps into scientific territory. If it's structured such that any observation is compatible with being in a simulation, if it's fundamentally unfalsifiable, then it's more of a philosophical stance. Some thinkers have tried to extract empirical tests. For example, certain lattice-like predictions of a discrete underlying space could manifest as energy-dependent anomalies in the propagation of particles. Others have suggested that limits in computational resources might show up as unexpected symmetries or constraints in particle physics. Yet so far, the best evidence we have points toward a smooth, well-described continuum at the scales we can probe, with the exceptions expected from quantum phenomena. The hunt continues in particle physics and quantum gravity research. If space and time are emergent from deeper layers of reality, as some approaches to quantum gravity propose, then those layers might leave subtle fingerprints we could, in principle, detect. Another way to look at it is to consider what it would mean socially and ethically if we were in a simulation. Would it change how we live? On the one hand, nothing about everyday cause and effect changes. Gravity still pulls, stars still shine, and medicine that helps does so regardless of the cosmic substrate. On the other hand, some people worry that believing we're simulated could encourage fatalism or nihilism. Others find it liberating or exhilarating, a new way to frame questions about meaning, purpose, and creativity. But these are personal and cultural reactions rather than scientific evidence. It's worth noting that humans are predisposed to find patterns and agency, sometimes even where none exists. We evolved to infer causes. Did that rustle come from wind or a predator? So we naturally tilt toward hypotheses that attribute design or intention to puzzling phenomena. That tendency can be useful, but also misleading when applied to cosmic questions. The simulation hypothesis taps into that intuitive tendency. It's familiar to think of worlds created by minds because we ourselves create simulations and virtual environments. But intuition is only a starting point. Science demands testable claims and rigorous comparison with alternatives. Going back to inflation and the observable universe helps ground the discussion in concrete science. The theory of inflation was not invented to be neat and mysterious. It was proposed to solve specific puzzles about initial conditions and to make predictions about fluctuations. Those predictions were tested and refined by successive measurements of the CMB and large-scale structure. The tiny temperature ripples in the microwave background are not random noise. They match the statistical patterns predicted by inflationary models. These patterns are encoded as a spectrum of fluctuations where certain scales have more power than others. Satellites like Planck measured this spectrum with high precision, and inflationary models that produce the observed pattern are favored. That doesn't tell us everything. There are many versions of inflationary models, and physicists are still working to connect inflation to a deeper theory, perhaps related to particle physics at high energies. People sometimes wonder whether the earliest stages of inflation could have produced other pocket universes with different laws. That idea is called eternal inflation. In some versions, the inflationary process never stops in much of space, and separate regions bubble off and stop inflating, producing their own local universes with potentially different constants or physical laws. That's one way to get a multiverse, and if such regions are real, they would be forever beyond our observable horizon. It's important to understand that the multiverse is an inference from certain inflationary models and not a direct observation. It's a hypothesis that some physicists take seriously because it flows naturally from certain equations, but it raises tough questions about testability. How do you test for regions you can never see? Cosmologists tackle these sorts of challenges by looking for indirect signatures and internal consistency. For example, a particular inflationary model might predict a characteristic imprint in the polarization of the CMB, known as B-mode polarization, produced by primordial gravitational waves. Detecting that signature would be a major boost for inflation and could narrow down which models are plausible. Experiments in the coming years, from ground-based telescopes to balloon-borne instruments and next-generation satellites, are hunting for such signals. The detection would not only reinforce the inflationary picture, but also help bridge to particle physics and our understanding of the earliest moments after the Big Bang. Where does this leave us with the simulation idea? It's an intriguing intellectual exercise that raises real questions about probability, computation, and the nature of consciousness. But from a scientific standpoint, it's still largely speculative. The universe we map with telescopes and particle accelerators behaves in ways anybody would call physical. Its laws are consistent across vast distances and timescales and make accurate predictions. If there is a deeper substrate that makes the cosmos a simulation, it either reproduces those physical rules to a high fidelity, or it imposes them by design. In the first case, distinguishing between the real and the simulated might be practically impossible. In the second case, designers of the simulation would have intentionally chosen the rules we observe. There's a useful parallel in computational thinking. When a program runs on a computer, its laws are whatever the programmer coded. But programmers also build efficient systems and don't represent every atom. They create abstractions and only compute what's needed. If a simulated universe were constructed similarly, it could look perfectly continuous and law-like to its inhabitants while actually being very economical behind the scenes. That idea keeps the simulation possibility alive, but also makes it hard to test. The simulation could be intentionally indistinguishable. One place where the simulation idea becomes concrete is in thought experiments about making simulations ourselves. Suppose humanity, or our descendants, reaches a technological level where they can reliably simulate large, complex systems that include conscious agents. What would motivate them to do that? Curiosity, entertainment, scientific research, moral contemplation, or reasons we can't predict. If such simulations are feasible and desirable, then Bostrom's counting argument gains traction. If, however, technological or ethical barriers prevent civilizations from running such simulations in large numbers, then the argument weakens. At the practical edge of science, cosmologists continue their search for further clues about the early universe, and those clues could indirectly bear on some of the philosophical questions. Improved measurements of the CMB, surveys of galaxy distributions, studies of gravitational waves, and experiments probing the nature of dark matter and dark energy all refine our picture. For example, mapping how structure grows over time helps constrain models of dark energy and inflation. If we someday detect primordial gravitational waves, we'd know the energy scale of inflation and gain insight into physics near the Planck scale. Those insights could either tighten the standard cosmological model or reveal anomalies that force us to revise our assumptions. On a more speculative front, some researchers working on quantum gravity, attempts to unite general relativity with quantum mechanics, suggest space and time might be emergent phenomena. In such theories, the smooth fabric of space we experience would be a large-scale manifestation of more fundamental degrees of freedom, much like the way fluid behavior emerges from the interactions of many molecules. If that's true, there would be a new set of atoms of space and corresponding rules. Searching for the fingerprints of emergence is an active area of research. Does space have a smallest scale? Does information play a fundamental role in spacetime? Those questions are technical, but they overlap with the kinds of ideas tossed around in simulation debates. If spacetime is emergent, then the universe is less like a block of marble and more like a software system built on top of something deeper, though that something deeper may still be physical in its own right, not metaphorical. The observation that we can describe the universe with mathematics is another facet of this conversation. Why is math so effective? Some take its effectiveness as a hint that the universe has a structured, law-like nature that could, in principle, be encoded. Others caution that math is precisely the tool we develop to capture patterns, so of course it maps onto the world's regularities. The simulation hypothesis leans on this argument for intuitive appeal. If the universe runs by rules, maybe those are rules in a code. But again, that's philosophical framing more than empirical evidence. If you're wondering whether any of these ideas should change how you live, the short answer is probably not in a practical sense. Whether or not there's a metaphysical substrate beneath physical reality, the proximate rules, electromagnetism, chemistry, gravity, govern what you can do, what medicines work, and what technologies are possible. Even if the cosmos were a simulation, the consequences of acting as if physical laws are real remain the same. That pragmatic stance is why most scientists treat these philosophical questions as interesting, but separate from the hard work of measurement and model building. Still, the human impulse to ask what's really going on is powerful and productive. It pushes people to explore new ideas, to design clever experiments, and to refine our models. That's how inflation moved from a speculative idea to a central piece of modern cosmology. Someone proposed it to solve real problems. It made predictions, and observers checked those predictions. That mix of creative thinking and empirical testing is the engine of science. So, if the observable universe is a bubble defined by light travel time and expansion, and inflation explains how that bubble got so uniform and why structures formed, how do we build the next set of tests? Which observations could separate competing ideas about the early universe? And when it comes to simulation, what would meaningful tests even look like? Those are the next questions researchers are wrestling with, using ever more sensitive instruments and more imaginative theoretical work to push the horizon of what we can know. If you want to turn the simulation idea into something you can actually test, the first thing to do is ask, what would a simulated universe look like from the inside? Imagine you're playing a video game. The world looks continuous to you as you run around, but if you zoom in and examine the texture maps, the polygons, or the grid the engine uses, you'll eventually find the seams and the shortcuts the programmers put in to save time and computing power. That suggests a few concrete possibilities for a real-world test. Look for seams, look for limits, and look for signs that certain regions are being calculated only when they matter. One kind of seam people have proposed looking for is a fundamental discreteness to space or time. Our best theories treat space as smooth down to the scales we can probe, but several approaches to quantum gravity predict that at some unimaginably small scale, around the Planck length, 10⁻35 meters, space might not be continuous. If space is made of tiny chunks, then certain processes should behave differently at very high energies, and these differences could be detectable. For instance, some ideas predict that very high-energy photons would travel at slightly different speeds than low-energy ones, producing a tiny delay that accumulates over cosmological distances. Astronomers have looked for this using fast flashes from distant objects. Gamma-ray bursts and pulsars provide natural clocks, and so far the universe looks stubbornly smooth. No energy-dependent delays have been convincingly seen at the expected levels. That doesn't rule out all discrete models, but it does push the scale of any discreteness to even tinier sizes or force the discreteness to be arranged in ways that hide its effects. Another possible sign of a simulation would be a limit on how much information a region can contain or how finely information can be stored, like a resolution limit inside a rendering engine. In physics, this idea appears in the form of black hole entropy and the holographic principle. Physicists discovered that the maximum amount of information you can pack into a region of space seems to scale with the surface area of its boundary, not with the volume inside. That's a strange and powerful result. A black hole's entropy is proportional to the area of its event horizon, measured in Planck units. The holographic principle generalizes that idea and suggests that, in some circumstances, the information in a volume of space can be fully represented on a lower dimensional boundary. This is weird because our everyday intuition says three-dimensional things have information that scales with volume, but quantum gravity hints that nature may be much more economical. Holography has turned into concrete math in certain settings, most famously in the ADS/CFT correspondence developed in the late 1990s. In that framework, a gravitational universe living in a certain kind of space, anti-de Sitter space, is exactly equivalent to a non-gravitational quantum field theory defined on the boundary, a precise mapping between two different descriptions. It's the closest thing science has to a worked example showing how a spacetime could emerge from an underlying information-theoretic description. Caveats apply. ADS/CFT describes a universe with a negative curvature that doesn't match our roughly flat, dark energy-dominated cosmos. Still, it gives proof of concept that space as a derived thing is not just philosophy, it's an idea you can write equations for. If our universe is emergent from more fundamental information, that would bear at least a family resemblance to the idea that reality is, in some sense, encoded. Another technical angle that occasionally leaks into popular discussions is the suggestion that the universe might show patterns consistent with a compact topology, a kind of wraparound space. If you live on a surface where opposite edges glue together, a straight line can loop back around and meet itself. In 3 dimensions, there are analogous possibilities. The universe could be finite yet unbounded, with a topology that causes light to circle around. That would produce repeated images of distant objects and characteristic patterns in the microwave background. The so-called matched circles test where parts of the sky should show identical patterns, because they're really the same region seen from different directions. Cosmologists have searched for such patterns in CMB maps and galaxy surveys. So far, no convincing repeats have been found at scales below our observable limit, which means if the universe wraps around, its scale is at least comparable to the size of our observable patch or larger. Beyond these structural checks, there's the pace of change argument. If a simulation has limited computational resources, perhaps it economizes by only updating regions where observers are present. That would imply a kind of observer-dependent reality, which is a dangerous and philosophically loaded suggestion because it touches on consciousness. Still, we can ask simpler operational questions. Do physical processes behave the same way whether or not observers are around? All experiments so far suggest yes. Atoms and fields evolve according to unobserved rules just as predictably as when we look. If a simulation selectively treated observed regions differently, it would have to be unimaginably subtle to escape detection. More likely, if an advanced simulator wanted their simulated beings to have the illusion of a coherent world, they'd run the world autonomously, not as a lazy, on-demand render. Now let's step back from, can we catch the simulator, and look at a different kind of limit. How far can human knowledge reach? Cosmology has natural barriers set by causality and horizons, but there are also conceptual limits, questions that might always remain in the domain of philosophy because they don't change the empirical predictions. The simulation question is partly in that category. If the putative simulator arranges the laws and initial conditions so that the internal physics exactly match what we observe, then whether there is a deeper substrate becomes a matter of labeling. You can call the substrate real and the physics emergent, or vice versa. From an empirical perspective, 2 models that give identical observational predictions are indistinguishable. That's a familiar situation in physics. Multiple formulations, different metaphysical commitments, same predictions. It doesn't mean the metaphysical question is meaningless. It might be crucial for other reasons. But it does mean that science, as practiced, focuses on differences that produce testable variation. That philosophical point helps explain why most physicists treat the simulation idea with polite curiosity rather than enthusiastic pursuit. Science advances by narrowing down models that differ in measurable ways. The inflationary paradigm, for example, made testable predictions about the spectrum of primordial fluctuations, and those predictions could be compared to data. The simulation claim, as usually presented, is more like a wrapper. If the wrapper produces exactly the same inner content as an ordinary physical theory, there is nothing empirical to test. On the other hand, if you assert, we are in a simulation, and therefore X must be true and Y must be false, and those claims produce concrete differences in observations, then suddenly you've got a scientific hypothesis. Because of that, the more interesting versions of the simulation idea are the ones that do make testable claims. For example, if the universe is simulated on a lattice, there should be preferred directions or anisotropies imprinted at high energies, like the patterns you see when a painter uses a brush in a repeated way. Physicists have looked for violations of Lorentz invariance, the principle that the laws of physics are the same regardless of your state of uniform motion, because a discrete substrate could pick out a preferred frame. Experiments testing Lorentz symmetry have become extremely precise. They examine the behavior of particles, clocks, and light across many contexts and energy scales. To date, Lorentz symmetry holds to very high accuracy, which constrains simple lattice-style simulations. That pushes any hypothetical grid to scales beyond current detection. Another concrete area where cosmology and deep metaphysical questions intersect is the multiverse. Certain inflationary models and some ideas in string theory suggest that our observable universe might be one pocket among many, each with different values for fundamental constants. If there are many universes with different properties, then the fact that we observe life-permitting values becomes less surprising, because observers can only arise where conditions allow. That's the anthropic argument. Some interpret this as evidence for design or simulation. If many universes exist, it's easier to explain why ours looks tuned. But the multiverse idea itself sits in a tricky place scientifically. Some versions are consequences of equations and could, in principle, leave indirect signatures. Others are effectively untestable because their different regions are forever causally disconnected from us. One famous observational puzzle that ties into both the multiverse and simulation conversations is fine-tuning. Several constants of physics, say the strength of the electromagnetic force, the masses of elementary particles, the cosmological constant, seem to lie in narrow ranges compatible with complex chemistry and long-lived stars. Small changes in some of these numbers would make life, as we know it, impossible. Fine-tuning can be read in many ways, as a brute fact that invites a deeper physical explanation, as an anthropic selection effect in a multiverse, as evidence of intentional calibration, or as a mixture of these. Scientists try to move beyond hand-waving by calculating how sensitive certain outcomes are to parameter changes and by exploring mechanisms that naturally produce the observed values. For instance, the cosmological constant problem, why the observed vacuum energy is so small compared to theoretical expectations, remains a central mystery. Some proposed solutions invoke dynamics that relax the vacuum energy, others appeal to selection effects, and yet others explore new kinds of symmetry or particle physics. None of these answers require a simulation, but they show the kinds of concrete puzzles that drive research. A related thought experiment that often appears in this territory is the Boltzmann brain problem. In some cosmological models, especially those with eternal inflation or thermal fluctuations over enormous timescales, it's possible that random fluctuations could create a single brain with false memories. If such Boltzmann brains are much more common than ordinary observers like us, then typical observers would be these momentary fluctuations, and our observed history would be overwhelmingly unlikely. That's a reductio ad absurdum for those models. If they predict an absurd abundance of Boltzmann brains, we should reject them. The Boltzmann brain paradox forces cosmologists to refine models so that ordinary observers remain the typical case. The simulation analogy is that some frameworks produce absurdly many simulations of minds without coherent histories, and those frameworks are unsatisfactory because they don't match our experience of a consistent past. As cosmologists and physicists refine models, they use a familiar toolbox, make a theoretical proposal, work out its observational consequences, then look for those signatures with telescopes, accelerators, and clever data analysis. In the last decade and beyond, observational cosmology has exploded with new data. Large galaxy surveys map the distribution of matter over vast volumes. Microwave background telescopes measure temperature and polarization with exquisite precision. And gravitational wave detectors have opened an entirely new way to listen to the universe. These instruments don't target the simulation hypothesis per se, but they do constrain the space of possible cosmologies and the microscopic theories that could underlie them. For example, a precise detection of primordial gravitational waves would pin down the energy scale of inflation, which in turn would narrow candidate high-energy theories. If a particular high-energy theory had unique implications for space's microstructure, then the gravitational wave detection could indirectly inform debates about discreteness or emergence. Quantum mechanics also plays a starring role in these conversations. At the smallest scales, nature behaves probabilistically in ways that frustrate simple mechanical intuitions. Some thinkers see quantum randomness as a challenge to the simulation idea. If outcomes are genuinely indeterminate, what does a simulation do? One answer is that a simulation could implement genuine randomness via a hardware-level quantum process, like using a physical quantum random number generator, in which case the simulation's randomness is indistinguishable from nature's. Another answer is that what we call quantum randomness could be a feature of an underlying deterministic substrate, with apparent randomness emerging from hidden degrees of freedom or chaotic behavior. Both positions are debated within physics and philosophy. The important point is practical. Quantum mechanics gives us precise predictions and experiments. Any simulation-like model must reproduce those predictions or provide an alternative that fits the data at least as well. There are also interesting crossovers between information theory and spacetime itself. Some researchers argue that entanglement, a hallmark of quantum mechanics where particles share correlations that can't be explained classically, might be the glue that builds space. Work by physicists like Mark van Romsenduk and later developments in quantum gravity suggest that patterns of entanglement might determine distance and geometry. If true, the universe would resemble a kind of network of information with geometry emerging from connectivity. This doesn't mean the universe is literally a computer simulation, but it does shift the language. Physics becomes about information and relationships rather than things in space. That shift is compatible with the idea that reality might have a description akin to code, but again, it's a matter of description rather than decisive proof. It's worth emphasizing that searching for fundamental discreteness, or for anomalies that point to a deeper layer, is not motivated solely by curiosity about simulations. Those searches aim to learn how gravity and quantum mechanics fit together, one of the central unsolved puzzles in physics. Any viable theory of quantum gravity might render space and time as emergent, discrete, or something else entirely. The difference between seeking evidence for quantum gravity and seeking evidence of a simulation is one of framing. The former treats nature as an object of study that may have unexpected structure. The latter interprets that structure as the footprint of an external designer or computation. Scientists operate comfortably in the first framing because it leads to equations, experiments, and testable predictions. If we pivot back to more everyday concerns, it's natural to ask whether any of this changes how we live. Practically speaking, not much. Whether or not the cosmos has a deeper substrate, the proximate physical rules, mechanics, electromagnetism, thermodynamics, remain the tools we use to predict outcomes, design technology, and heal illness. Medicine works because chemistry works. Airplanes fly because fluid dynamics and structural mechanics are reliable. Your phone works because semiconductors obey quantum rules. Even if all of this runs on a deeper layer of reality, the immediate cause-and effect that organizes our lives stays the same. That's why many scientists treat the simulation question as intellectually interesting, but separate from the job of doing physics. The social and psychological responses to the idea are varied. Some people find the possibility that the universe might be a simulation disquieting. Others find it oddly comforting. Historically, humans have long entertained models where reality is a dream, a story, or the creation of a higher intelligence. The modern simulation discussion is a technology-flavored version of that old impulse. Its novelty is that it uses current understanding of computation, consciousness, and cosmology to frame claims about probability and consistency. It invites us to imagine not just gods or spirits, but engineers and programmers. That imaginative leap can be entertaining and thought-provoking, but it's not the same thing as a scientific explanation. Another reason the simulation idea has traction is that it makes certain metaphysical worries explicit. Questions about why does anything exist, or why these laws and not others, are hard to address within physics because physics describes regularities and mechanisms rather than ultimate reasons. The simulation picture offers one kind of why. The universe exists because someone or something set it up that way. But it's worth noting that this answer just relocates the ultimate question one level up. Why does the simulator exist? What laws govern the simulator? If you can always posit a higher-level system, you can defer the ultimate explanation indefinitely. That regress doesn't make the simulation false. It shows that some questions about origins might always be pushed back. Meanwhile, scientific work presses on. Researchers are planning and building new instruments that will refine our picture of the early universe and the behavior of matter and energy at extreme conditions. Projects like next-generation CMB experiments, large-scale galaxy surveys, gravitational wave observatories spanning a wider frequency range, and particle accelerators, or tabletop experiments probing new physics, all target different pieces of the big puzzle. Each new, precise measurement tightens the constraints on theoretical space. It rules out some models, highlights anomalies that need explanation, and often spurs creative theoretical work to reconcile new data with existing frameworks. Anomalies are particularly interesting because they're where revolution often starts. When careful observation finds a discrepancy with accepted theory, physicists take note. Sometimes the discrepancy fades away with better calibration or more data. Sometimes it survives and leads to new understanding. The discovery that the expansion of the universe is accelerating, for instance, came as a surprise and forced cosmologists to introduce dark energy into their models. If future data revealed something equally unexpected, a robust violation of a core symmetry, a reproducible anomaly in how particles propagate, or a pattern in the CMB inconsistent with inflation, it would trigger a search for deeper explanations, possibly even ones that change how we think about space, time, or information. If you like puzzles, the cosmological questions are irresistible because they mix the very large and the very small, the mathematical and the experiential. The challenge is to keep curiosity honest, to ask bold questions but demand testable answers. The simulation hypothesis is a spectacularly bold question because it touches on the nature of reality itself. It's a useful intellectual tool because it forces us to confront assumptions about typicality, computation, and information. But for it to become part of physics proper, it needs to be sharpened into specific, testable claims. Some thinkers have attempted that sharpening, but as yet there is no consensus test that would decisively confirm or falsify the general simulation claim. There's also a healthy humility built into modern cosmology. We know an enormous amount, in the sense that we can calculate the growth of structure, the abundances of light elements from the first few minutes, and the statistical properties of the microwave background. But we know far less about why certain parameters have the values they do, or about the true quantum nature of spacetime. We should expect that new theories will challenge existing intuitions. That means staying open to surprising ideas while holding them to observational standards. One of the more subtle but profound realizations from recent theoretical work is that information plays a central role in physical law. Whether that's through black hole entropy, the holographic principle, or the idea that entanglement patterns knit together space, information seems to be more than an interpretive tool. It might be part of the furniture of the universe. That observation makes the simulation analogy compelling at a poetic level. Both frames put information at the base. But again, it's a similarity of description more than proof of an underlying computational process run by external minds. As instruments and theory both improve, our telescopes and detectors gain sensitivity to signatures that were previously invisible. That means the question of whether the universe bears any telltale signs of a deeper structure is increasingly empirical rather than purely speculative. Tests that once seemed impossible, probing inflation's fingerprints via the polarization of the CMB, detecting faint gravitational waves from the earliest moments, mapping vast swaths of cosmic structure with unprecedented detail, are within technological reach. Each of these measurements tightens the constraints on models and opens new windows onto fundamental physics. If a dramatic signature that looked like a rendering artifact were found and could not be explained by conventional physics, it would trigger intense debate and scrutiny. Extraordinary claims require extraordinary evidence. Anomalies get checked, rechecked, and tested against many possible mundane explanations. That's the cautious, conservative heart of science. It's less interested in sensational metaphysical conclusions than in building a consistent, predictive account of observations. If a simulation-like artifact survived that gauntlet, it would be a revolutionary discovery. Until then, the balance of evidence keeps us working with the physical laws as they present themselves. So when people ask whether we're living in a cosmic illusion, the best short answer is that it's a question worth thinking about, but it's not a substitute for the kind of precise, testable modeling that gets results. The simulation idea channels familiar intuitions about design and computation, and it points to real scientific themes: information, emergence, and the relationship between micro and macro descriptions. But it also raises philosophical puzzles about explanation and infinity that science alone may struggle to settle. While we continue to refine instruments and equations, there's a practical way to treat the question. Investigate what can be investigated. Push measurements where they can discriminate between models. Build theories that make clear, testable predictions, and keep an open but skeptical stance toward metaphysical conclusions that go beyond the reach of data. That approach has a strong track record. Ideas that started as speculative, like inflation, became central because they solved concrete puzzles and made predictions that could be checked. If the simulation idea is to join that tradition, it will need a similar path. Tie the speculation to specific consequences, and then look for those consequences in the world. In the meantime, the story of cosmology is still full of discovery. We're learning to read cosmic fossils, test the structure of spacetime at ever more delicate levels, and wrestle with profound questions about information, emergence, and typicality. Those pursuits give us more than answers to abstract metaphysical problems. They supply the practical knowledge that improves lives through technology, communication, and medicine. Whether or not there's an external simulator, the enterprise of science, hypothesize, predict, observe, revise, continues to expand what we can reliably say about the universe we inhabit. If the goal is to sharpen these big-picture ideas into concrete science, the next step is to be specific about where to look and what counts as a signal. There are several complementary lines of inquiry. Some sit squarely in the realm of cosmology and particle physics, some come from quantum information theory, and some are philosophical or ethical but still tied to real-world choices. All of them help us move from playful speculation toward testable claims, and that's where progress happens. One obvious place to keep watching is the cosmic microwave background. That faint afterglow from the time the universe became transparent is a treasure trove of information about the early universe. We already use it to constrain inflationary models and to measure the content of the cosmos. But it can also harbor subtler fingerprints, tiny anomalies in the pattern of fluctuations, unexpected correlations in polarization, or signs of non-Gaussianity. Patterns that aren't purely random could point toward specific physics of the earliest moments. If, for example, inflation was driven by a particular kind of field or happened at a particular energy scale, those choices can leave telltale marks in the spectrum and polarization of the CMB. High-precision measurements from ground-based telescopes and planned satellite missions are pushing those limits. Finding anything that departs from the simplest inflationary predictions would be big news, not necessarily a smoking gun for a simulation, but very likely a clue that we need a new underlying theory. Gravitational waves open another window. We've entered a new era where spacetime itself can be listened to. The gravitational waves detected so far come from colliding black holes and neutron stars, events that happen relatively late in cosmic history. But there's also the possibility of a primordial gravitational wave background, faint ripples produced in the earliest fractions of a second, perhaps by inflation itself. Detecting those primordial waves would not only pin down the energy scale of inflation, but also constrain candidate theories of high-energy physics, narrowing the possibilities for what the microphysics of spacetime could look like. If any of those signatures were inconsistent with a smooth classical spacetime, then theorists would scramble to build models that explain the anomaly. Again, not proof of a simulation, but the kind of unexpected result that forces new thinking. Particle physics and precision tests of symmetries are equally important. Many proposals for discrete or emergent space predict, in some form, violations of cherished symmetries like Lorentz invariance, the idea that the laws of physics are the same for all observers moving at constant velocity. Tiny violations would show up as minute differences in how particles behave at high energies or in the propagation of light over cosmological distances. Experiments with atomic clocks, particle accelerators, and astrophysical observations of distant gamma-ray bursts and pulsars place incredibly tight bounds on such violations already. Those constraints don't falsify every discrete or emergent model, but they push any potential grid or underlying structure to scales finer than those experiments can see. There have been specific claims worth mentioning because they illustrate how an anomaly gets translated into science. Around a decade ago, a pair of theorists suggested that a type of holographic noise might be measurable with certain gravitational wave detectors, and an instrument called G-O600 reported an unexplained noise at the time. That coincidence sparked excitement and a flurry of papers exploring whether the noise could be a signature of fundamental limits on position measurement. Subsequent work, however, attributed the signal to more prosaic instrumental effects, and the case faded. That episode is instructive because it shows the way the scientific method works. Someone proposes a bold possibility, experimentalists check their instruments, theorists propose alternative explanations, and the community converges on the most plausible account. Extraordinary claims require a high burden of proof, and rightfully so. Another promising theoretical insight comes from quantum information. Over the past couple of decades, physicists have started thinking about entanglement and information as not just properties of quantum systems, but as ingredients that might build spacetime itself. In certain solvable models, patterns of entanglement correspond to geometry. More entanglement between two subsystems can mean they are closer in an emergent spatial sense. That's a concrete result in simplified settings, and it suggests a tantalizing picture. Space might be a kind of bookkeeping device for information relationships. If that picture survives rigorous extension to realistic cosmologies, it would change how we frame questions about whether reality is like code. Instead of the metaphor of a programmer writing lines of code, the deeper description might be about networks and information flow, something more abstract but amenable to mathematical analysis. Linked to that is the black hole information puzzle, which has been an engine for new ideas. Black holes have entropy proportional to the area of their horizon, and Hawking radiation seemed to suggest that information that falls into a black hole would be lost forever, violating quantum mechanics. Over decades, this tension produced new concepts, like holography and the idea that information is somehow preserved in subtle correlations. Recent advances, including calculations of entanglement entropy using so-called islands, have shown that the evaporation of black holes can be consistent with unitarity, the idea that quantum information is conserved. Those results are highly technical, but the takeaway is that deep questions about information in extreme gravitational settings are tractable and lead to concrete predictions about entropy and correlations. They suggest the possibility that the building blocks of spacetime are fundamentally informational, not just material. That has a philosophical resemblance to simulation talk, but it's grounded in explicit equations and checkable consequences. There's also a rich set of ideas about what the discrete alternatives to continuous spacetime might look like. Loop quantum gravity, causal dynamical triangulations, and causal set theory each propose different pictures where spacetime emerges from more primitive elements. Think nodes and links or small building blocks that join in rules to make continuum geometry at large scales. These approaches make different technical predictions about how geometry fluctuates at the smallest scales and how that might influence particle propagation or black hole behavior. Translating those predictions into observable effects is hard because the relevant scales are tiny, but theorists keep working to identify possible windows where quantum gravitational signatures could be amplified or leave indirect fingerprints. A practical limit to all of this is cosmic variance and horizon restrictions. No matter how good our instruments become, there are fundamental statistical limits in cosmology. We observe one universe from one vantage point, and for some large-scale modes, there are only a few independent samples available. That means some questions about initial conditions may be forever uncertain because we cannot generate a larger statistical ensemble of universes. Similarly, the causal horizon, the limit set by the speed of light and the finite age of the universe, means we can never observe regions beyond our bubble. If a multiverse exists with regions that have different laws, those regions might be unobservable in principle. Those are not merely technical obstacles. They are built into the geometry of spacetime and place real constraints on how far empirical science can push. Let's switch gears and talk about consciousness, because the most provocative version of the simulation discussion hinges on whether simulated systems can be conscious. There are a few distinct positions here. One is functionalism. Mental states are defined by their functional roles, what they do, how they process information. So if you reproduce those roles in a different substrate, silicon, instead of biology, you reproduce the mental states. Under functionalism, a sufficiently detailed simulation of a brain could, in principle, be conscious. That's the position that makes Bostrom's counting argument plausible. If simulated minds are real minds, many of them could exist in a future computational civilization. Another position is that substrate matters, that consciousness depends on specific biological or quantum properties of brains that a simulation cannot duplicate. This is a harder position to test, because it requires a detailed account of what those properties are and why they generate subjective experience. Philosophers and neuroscientists debate this fiercely. There are also intermediate views, like integrated information theory, IIT, which attempts to quantify consciousness as a particular measure of information integration. IIT offers a concrete metric that might be computed for physical systems, which could in principle distinguish conscious systems from non-conscious ones. But whether IIT is the right account is unsettled. Why does any of this matter beyond philosophical curiosity? Because it affects how we count minds in any probability argument. If consciousness is substrate-independent and cheap to generate, then speculative future civilizations could run enormous numbers of simulations. If not, the production of conscious simulations might be rare or impossible. That uncertainty is a major reason why the simulation argument remains a probabilistic trilemma rather than a proof. There's also an ethical angle that's showing up in contemporary debates. As artificial intelligence systems get more sophisticated, we already face questions about whether they have moral status, how we should treat them, and whether we should create systems capable of suffering. Those are immediate, concrete issues with practical consequences for policy and research. The broader cosmological question, are we already inside a simulation, has more abstract ethical implications, like whether simulated creators have obligations to their creations. But those philosophical questions feed back into present-day choices. If creating simulated minds is morally fraught, perhaps advanced civilizations would refrain from running ancestor simulations, weakening Bostrom's assumptions. These ethical considerations are not peripheral. They potentially shape the future technological landscape that figures into the statistical arguments. Another practical set of tests concerns the possibility of rendering shortcuts, places where a simulator might economize by approximating physics unless an observer probes the system. In our world, we don't see behavior that depends on observation. Atoms evolve fine whether or not someone watches them. But there are well-known quantum puzzles about measurement and the role of observers. Some interpretations of quantum mechanics give a special role to measurement, which prompts imaginative people to ask whether measurement itself could be a clue to a rendering process. The mainstream scientific approach is to treat these as interpretations rather than distinct physical theories, different ways of talking about the same predictions. If a simulator imposed observer-dependent shortcuts that led to new, testable deviations from standard quantum predictions, we could in principle detect them. So far, experiments uphold quantum predictions to astonishing precision. One of the more concrete routes to narrowing possibilities is to think in terms of falsifiable predictions. Take Lorentz symmetry again. Suppose someone models a simulated universe on a cubic grid. That grid picks out preferred directions, which would break Lorentz invariance at some scale, and should be measurable as anisotropies or energy-dependent effects in particle propagation. Experiments have placed extremely tight bounds on violations, so simple cubic grid models become implausible. That doesn't eliminate the simulation concept altogether, but it constrains the kinds of simulations that could reproduce our observations. Another testable idea is whether the fundamental constants might vary in space or time. If they did, it could indicate that the physical laws aren't fixed by fundamental necessity, but by contingent choices, or that the underlying structure permits local variation. Astronomers look for changes in the fine structure constant and other dimensionless quantities using quasar spectra and laboratory clocks. So far, observations are consistent with constants being constant to very high precision, which favors models with fixed underlying laws. A more speculative but mathematically crisp possibility is that the universe's initial conditions are special in ways inconsistent with random processes. Inflation explains a lot of the initial regularity, but physicists still debate the probability distribution of initial states and whether some dynamical mechanism selects special conditions. If one could show that the initial state was implausibly fine-tuned under all reasonable physical processes, it would motivate alternative explanations. Some people might point from that to simulation, but other routes, new dynamical principles, selection effects, or unknown physical mechanisms, are equally plausible. Again, what matters for science is whether those alternative explanations can be formalized and compared to data. We should also keep an eye on developments in quantum technologies and computing. If we, as a species, get much better at simulating complex systems, brains, woven ecosystems, or entire virtual environments, we will learn practically what is required to generate lifelike agents. We'll also face the ethical questions mentioned earlier about whether it is acceptable to run simulations that might produce suffering. Those developments, when they come to pass, will inform debates about what is technologically feasible and culturally acceptable in potential simulator civilizations. In other words, we don't need to settle metaphysical debates to make progress. Watching how our computational power and values evolve gives us empirical input for the probability assessments that Bostrom-style arguments rely on. Another set of real, testable physics questions comes from the study of high-energy cosmic rays and gamma rays. These particles travel across cosmological distances and sometimes experience interactions or delays that could reveal fundamental properties of space. For instance, if space is dispersive at the smallest scales, meaning particles of different energies travel at slightly different speeds, then we could measure tiny time lags in signals from distant explosions. Astronomers have used gamma-ray bursts and flares from active galaxies as precisely timed beacons, and found no convincing dispersion at the levels that would indicate a simple discrete lattice. That pushes any such effects to even more minute scales, constraining models that imagine a coarse-grained substrate. The question of topology also stays interesting. If space wraps around in a compact way, if you could, in principle, travel in a straight line and return to your starting point, the sky would show repeated patterns. Searches in the microwave background for matched circles or repeated structures in galaxy surveys haven't found convincing evidence of a small wrapped universe, but those searches are sensitive only to scales comparable to our observable patch. If the wraparound scale is much larger, we won't detect it. That again emphasizes a recurring theme. Some hypotheses are in principle testable, others lie beyond observational reach and slip into metaphysics. At a deeper level, the simulation conversation is a reminder of an important epistemic point. Explanations come in different flavors. Some explain by mechanism. X produces Y through well-understood processes. Others explain by selection. Y is observed because only observers that see Y exist. The latter can be powerful but has limits. It can explain why we observe something without offering a mechanism that makes concrete predictions beyond the selection effect. The multiverse and anthropic reasoning exemplify selection-style explanations. The simulation hypothesis can be cast either as a selection argument, we're likely to be in a simulation if there are many of them, or as a causal mechanism, a simulator built the universe to serve some purpose. These are different claims with different implications for testability. Philosophy also contributes here by clarifying the sorts of claims that are meaningful in scientific terms. A hypothesis that predicts observable deviations from known physics is a scientific hypothesis. A hypothesis that can accommodate any possible observation by invoking inscrutable designer choices is not, strictly speaking, a scientific hypothesis because it cannot be falsified. That distinction is not a value judgment about the creativity or depth of the idea. It's a methodological guideline about what kinds of claims lead to empirical progress. Meanwhile, technology keeps delivering more data. Large-scale surveys map billions of galaxies now, and future projects aim to map most of the visible universe's structure with unprecedented detail through 21 cm cosmology. The radio signal of neutral hydrogen, weak gravitational lensing, tiny distortions of galaxy shapes by intervening mass, and deep spectroscopic mapping. Each new map tightens constraints on dark energy, dark matter, and the initial fluctuations. If any of those maps show anomalies that contradict the standard cosmological model, theorists will explore new physics that could explain them. A careful search for anomalies is, in effect, a search for cracks where deeper structure might peek through. A separate thread worth following is computational complexity and the limits it imposes. Even if conscious simulations are possible in principle, they might be computationally infeasible to run at the scale of entire universes. Some theorists argue that it's easier to simulate a subset of reality, like a brain or a lab environment, than an entire sky full of galaxies. That possibility reduces the plausibility of enormous numbers of full universe ancestor simulations, because a more efficient civilization might have better uses for resources than running huge numbers of detailed realities. On the other hand, if the goal of simulators is historical accuracy for certain experiments, they may only need to simulate the slice of reality relevant to those tests. The complexity argument is subtle and depends heavily on assumptions about what future computation can do and what future societies value. A related technical point is compression. Simulating reality is a problem of storing and evolving information. If the physical universe is highly compressible, if large swaths can be described by compact mathematical rules, then simulating them could be far cheaper than naive estimates suggest. That's the same trick game engines use. Compress the rules so they don't need to store every detail. Many physical systems are indeed compressible because of symmetries and conservation laws. That makes it harder to dismiss the simulation idea purely on computational cost grounds. The counterargument is that, while compression helps, certain aspects, like modeling biochemical interactions in brains at molecular resolution, may remain extremely costly. One more angle worth exploring is the possibility of indirect evidence in the kind of unexpected discoveries that have repeatedly reshaped physics. Historically, revolutionary ideas rarely begin as metaphysical claims. They start as anomalies, a spectral line that doesn't fit, a decay rate that's off, a missing mass in a cluster. Those anomalies force theorists to invent new frameworks. Dark matter and dark energy are modern examples. If something analogous appeared that defied all reasonable physical explanations, it might push the community to entertain more radical hypotheses, including ones that resemble the simulation picture. That's why the scientific community keeps a list of anomalies and treats them with serious attention. Sometimes they resolve into mundane calibration issues. Sometimes they lead to breakthroughs. Finally, it's useful to think about what kind of discovery would change widespread scientific practice. Finding a reproducible violation of a fundamental symmetry, or a new particle with unexpected properties, or a robust signal of primordial gravitational waves inconsistent with predicted models would alter the equations physicists write and the way they plan experiments. By contrast, discovering that we live in a simulation, in the sense that there's an external agency running a program, would be a different kind of discovery. It would raise metaphysical and perhaps theological questions that science isn't designed to answer alone. If such a thing were discovered through empirical means, the fallout would be enormous in every domain: science, philosophy, society. But given how science builds knowledge, incrementally, by narrowing models through observation, the route to any such radical conclusion would almost certainly run through a sequence of measurable anomalies and testable theoretical proposals. For now, the most productive posture is to keep doing the work that yields concrete, testable outcomes. Map the sky, listen for gravitational waves, push particle physics to higher sensitivity, and explore the theoretical space of quantum gravity and emergent spacetime. In parallel, philosophers, ethicists, and technologists should keep wrestling with the conceptual and moral issues that arise as we get better at building complex simulations and understanding consciousness. Those parallel activities inform each other. Better theories of mind sharpen how we interpret simulations. Better simulations teach us what it takes to create complex behavior. Better cosmological data constrain the possibilities for exotic physics. The interplay of these strands is where progress happens. With that in mind, it's worth looking ahead at some specific experiments and programs to watch. On the cosmology side, next-generation CMB telescopes and satellite proposals aim to probe polarization with unprecedented sensitivity. Those measurements target the signature of primordial gravitational waves. Large-scale structure surveys, optical, infrared, and radio, will provide three-dimensional maps of matter distribution across cosmic time, refining constraints on dark energy and initial conditions. Gravitational wave observatories operating at different frequency bands, including space-based detectors like the planned LISA mission, will broaden the types of sources we can detect and may one day be sensitive to a gravitational wave background from the early universe. Particle physics experiments, both large colliders and precision tabletop tests, keep pushing the energy and sensitivity frontiers. And in the laboratory, quantum information experiments, creating and manipulating entangled systems, measuring decoherence, and simulating quantum many-body systems, test the limits of quantum theory and may reveal how information underwrites physical behavior. None of these projects guarantees an answer to whether we live in a simulation, but each constrains the space of possibilities and sharpens the questions. That's the scientific way forward. Take an intriguing idea, translate it into concrete predictions or constraints, and measure the world to see which versions survive. Along the way, we learn more about the cosmos and ourselves, how complexity emerges, how information behaves, and what freedoms the laws of nature permit. There are deep philosophical questions here about explanation, typicality, and the nature of consciousness, and those will be debated for a long time. But for the curious and the careful, the immediate job is clear. Keep making observations, refine the math, and let the data guide the imagination. If you step back from the metaphors and the mind-bending scenarios, a useful way to organize the whole question is to separate three things: what we can measure, what we can plausibly infer from those measurements, and what remains speculation or philosophy. That sounds obvious, but it helps avoid getting swept up in seductive but untestable leaps. Science advances by narrowing the gap between measurement and inference. You make observations, build models that predict those observations, then use future observations to discriminate between models. The more a hypothesis makes concrete, falsifiable predictions, the more it behaves like science and the more quickly it will be accepted or rejected. So if someone asks, how would we ever know if our universe were a simulation? The practical answer is: look for predictions that a simulation model makes that differ from a non-simulation model, and then test them. That's easier said than done, because a sophisticated simulator could arrange for the internal physics to be indistinguishable from a regular physical substrate. But not all simulation ideas are equally subtle, and some concrete possibilities give us a strategy. One clear line of attack is to examine symmetries and invariances. Physics loves symmetry. Conservation of momentum comes from translational symmetry, conservation of energy from time translation symmetry, and so on. Many of the deepest physical laws are encoded in symmetries. A naive or crude simulation, think of a simple lattice grid used to model space, would likely break some of these symmetries at small scales. That would show up as preferred directions or energy-dependent changes in how particles move. Experimentalists have, therefore, tested symmetry principles to extreme precision. The absence of violations in many contexts constrains simple grid-like simulations. That doesn't rule out all simulation scenarios, but it forces any hypothetical simulation to reproduce symmetry to a very high degree, which in turn constrains its possible architecture. A second concrete place to look is information limits. Physics already gives us surprising statements about how much information a region of space can hold, black hole entropy being the canonical example. If space is emergent from information, then there might be limits or relationships that look more natural from an informational perspective than from a naive stuff-in-space perspective. The holographic principle, where a volume's information content is encoded on a lower dimensional boundary, is one expression of this. Holography isn't a smoking gun for a simulation, but it does show that nature may be far more economical with information than our naive intuition suggests. If the universe really is encoded in some way, then the patterns of correlations and entanglement might carry signatures of that encoding. Detecting those signatures is a difficult but active area of research. Another potential avenue is to exploit cosmic microscopes, natural phenomena that magnify tiny effects over great distances and times. Light and gravitational waves travel across the universe and carry tiny imprints of the medium they traverse. If space had a subtle granular structure, signals that travel over cosmological distances could accumulate minute distortions or delays. Astronomers use fast, repeatable events, gamma-ray bursts, pulsar timing, gravitational wave chirps, to look for frequency-dependent delays or dispersion effects. So far, most of these searches have come up empty or have placed strong limits on many simple discretization models. But as instruments improve and samples grow, the bounds get tighter and models have less wiggle room. Thinking in terms of resources gives another perspective. Simulating a whole universe at molecular or atomic fidelity would, by naive estimates, require unfathomable computing power. But practical simulations don't work that way. They compress, approximate, and only compute what matters to observers. Game engines show how this works in practice. A character only sees detailed textures on what's nearby. Distant scenery is low resolution or procedurally generated. If a simulator used similar tricks, it might only calculate high fidelity in regions and times where conscious agents exist and interact. That leads to a subtle expectation. Localized anomalies might appear when observers probe very complex, previously unencountered configurations. In practice, that's an awkward expectation to test. It also walks into thorny philosophical territory. Are observers privileged in the equations of physics? In mainstream physics, we expect the same laws to apply everywhere and at all times, whether or not anyone is watching. So far, experiments support that view. The atoms on your table behave predictably regardless of whether you're paying attention. Probability is another key ingredient. Bostrom's trilemma rests on counting minds and making assumptions about how likely advanced civilizations are to run many simulations. Bayesian reasoning, the formal method of updating probabilities in light of data, offers a way to formalize our uncertainty. We can set priors for how likely it is that civilizations reach a technological stage capable of massive simulations, and priors for how likely those civilizations are to choose to run simulations. As we learn more about the development of intelligence, the costs of computation, and the prevalence of life, those priors should change. The problem is we currently lack data on the very things that matter. We only have one example of a technological civilization, us, and we don't know how typical it is. That scarcity of data is why simulation discussions often end up as philosophical probability exercises rather than concrete physics. The reference class, problem and probability, appears here as well. When you say the typical observer, who do you include in that class? Do you count every possible moment of consciousness that could exist in all possible physical substrates? Do you restrict to observers with human-like continuity and memory? Different choices of reference class lead to wildly different conclusions about what is typical. Philosophers debate these issues because they matter for making predictions. If you assume simulated momentary minds, like Boltzmann brains, vastly outnumber long-lived, history-rich observers, you get paradoxical conclusions that conflict with our experience. That paradox drives cosmologists to prefer models where ordinary observers like us dominate the counting, which in practice means avoiding cosmological proposals that produce absurdly many fleeting observers. There's also a practical conversation to be had about ethics and the developing technologies that make simulation discussions less abstract. As AI systems get more complex and virtual environments grow more immersive, we are already confronted with real-world versions of the philosophical questions. If we build agents that display behaviors and internal structures suggestive of consciousness, do we owe them moral consideration? Are there constraints or regulations we should adopt to prevent large numbers of suffering minds from being created for entertainment or research? Those are immediate, actionable questions, not metaphysical speculations. The way future societies answer them will feed directly back into the plausibility of Bostrom-style arguments. If advanced civilizations prohibit ancestor simulations on ethical grounds, that reduces the expected number of such simulations and changes the statistical picture. Another practical route for thought is to examine where a simulation hypothesis would add explanatory value beyond existing physics. Remember, good scientific hypotheses often do two things. They explain something puzzling, and they make predictions you can test. The simulation idea can be compelling if it explains a real puzzle that other frameworks struggle with. For example, if we found a set of anomalies that resisted explanation for decades, patterns in the cosmic microwave background, inexplicable correlations in particle behavior, or a reproducible breakdown of a fundamental symmetry, then the simulation hypothesis might become one of several plausible explanations. But at present, the physical puzzles we face, dark matter, dark energy, the value of the cosmological constant, are problems that have natural extensions within physics and are being actively pursued with tools that have a track record of success. That doesn't make the simulation idea irrelevant. It just means the scientific community concentrates on explanations that can be formalized into the standard method of prediction and test. Let's go deeper into one of those active research strands, the relationship between entanglement and geometry. It's a good example of how a concept from information theory, entanglement, which describes weird quantum correlations, has moved from philosophical curiosity to a concrete research program that could tell us about how space itself might emerge. In certain solvable models, physicists can show mathematically that the pattern of entanglement among quantum degrees of freedom determines distances and even curvature in a dual spacetime. That's a precise statement in simplified settings, and it led to growing excitement. If geometry can arise from relationships among information-carrying elements, then the notion of space is no longer fundamental, it's emergent. That discovery doesn't imply an external programmer, but it does change how seriously we can entertain the idea that what appears to be physical law could be an emergent description of information processing rules. The fact that entanglement seems to be so central throws an interesting light on where signatures of deeper structure might show up. If space is woven by entanglement, then certain patterns in quantum correlations could indicate the presence of an underlying weave that deviates subtly from predictions based on naive continuum geometry. Detecting such deviations would be incredibly hard because quantum phenomena are hard enough to control and measure even in the lab. But advances in quantum technologies, more precise quantum sensors, larger entangled systems, and better control of decoherence will expand our ability to probe these effects. In principle, entanglement-based signatures could be some of the most direct evidence for emergence at the foundation of spacetime. Related to that is the surprising cross-pollination between quantum error correction, an engineering concept in quantum computing, and ideas in holography and emergent geometry. Quantum error correction is about protecting fragile quantum information from noise by encoding it redundantly across many qubits. In certain holographic models, the way information about a bulk region is encoded on a boundary resembles an error-correcting code. Local errors on the boundary don't necessarily destroy the encoded bulk information. That correspondence suggests that whatever the substrate of spacetime is, its stability against disturbances could be tied to redundancy and information-theoretic mechanisms, just like engineered quantum computers. This connection is technical, but its big-picture implication is that information-theoretic principles, not exotic metaphysical assumptions, could underlie the emergence of spacetime. That's one reason why talking about code is useful metaphorically, but can be misleading if taken too literally. The mathematical structures at play are about patterns of correlation and redundancy, which happen to be shared by both computer science and quantum gravity. One more angle that deserves attention is the role of anomaly hunting, looking for anomalies that persist under scrutiny. The history of physics shows that sustained anomalies, those that survive repeated experimental checks and can't be shoehorned into current theory, are where revolutions often begin. The discovery of the accelerating expansion of the universe is an instructive recent example. It started as an observational surprise and became an accepted part of cosmology only after independent teams verified the effect and theorists introduced dark energy as an explanatory concept. If something similarly persistent and inexplicable turned up that was suggestive of a discrete substrate or of some information-theoretic limitation, then the simulation idea would move from the speculative fringes into the mainstream of investigation. That's not to say the simulation hypothesis will be the answer. There could be other, more mundane explanations. But persistent anomalies force theorists to expand the space of models they take seriously. It's also worth reflecting on the temptation to anthropomorphize unknown causes. Humans are wired to infer agency and to imagine designers behind complex artifacts, because that's often the right inference for the kinds of environments our brains evolved in. We see intricacy and assume craftsmanship. That tendency can be productive. It led us to the idea that certain patterns in nature are best explained by underlying mechanisms rather than by chance. But it can also mislead. The universe contains many regularities that arise from simple natural processes, not agents. Newton's laws explain planetary motion without invoking a sky god, and Maxwell's equations explain electromagnetism without appealing to intentions. Sometimes the right move is to look for a mechanism, not a mind. The simulation idea often swaps one unexplained stack for another. Instead of asking why the physical laws are what they are, you ask why the simulator made those laws. That can be a meaningful question, but it's not automatically a better or more scientific one. A pragmatic way to keep the conversation honest is to ask, what would we do differently if we thought the simulation hypothesis were true? For most practical purposes, engineering, medicine, everyday reasoning, nothing changes. Electromagnetic forces still bind atoms, chemical reactions still follow thermodynamic constraints. Technologies that rely on these predictable rules will continue to function. The simulation idea becomes consequential only if it implies observable differences in the way those rules operate. If it doesn't, then the idea is metaphysical rather than scientific. If it does, then it's subject to the same tests as any other physical theory. It's tempting, though, to imagine a scenario where the simulator occasionally tweaks things in ways that matter, changing constants, inserting anomalies, or altering probabilities. That kind of dramatic speculation has little empirical support and creates difficult philosophical problems. Why would the simulator make such changes? How would we distinguish them from natural variation? And where would that leave the practice of science? The more you allow ad hoc tinkering by a simulator, the less predictive power science has, because any observation could be explained as the result of an outside intervention. That's why scientific methodology puts a premium on explanations that minimize ad hoc assumptions and maximize predictive scope. A final scientific point to consider is a methodological one. Testability is a spectrum, not a binary. Some ideas yield direct, immediate predictions that can be checked with existing instruments. Others produce indirect signatures that require new technology or better theory to interpret. Many productive research programs start in the latter category. String theory, for instance, produced a lot of mathematical structure before many direct experimental consequences were known. The simulation hypothesis sits mostly in the low testability region right now, but that doesn't mean it will stay there forever. The growth of quantum technology, improved cosmological surveys, and deeper theoretical understanding of information and gravity could, in principle, raise its testability. The right way to treat it scientifically is to try to sharpen it into proposals that bridge the gap between speculation and measurable consequence. As you think about all of this, it helps to hold two attitudes at once: healthy curiosity and healthy skepticism. Curiosity drives us to explore wild ideas and to ask big questions about the nature of reality. Skepticism keeps us honest about what counts as evidence and ensures we don't mistake imaginative coherence for empirical success. When both are in play, you get the best of science: imaginative models that are forced to answer to data. That interplay is how inflation moved from a speculative patch to the backbone of modern cosmology, and how quantum information ideas moved from abstractions to central players in quantum gravity research. So where does that leave the original question? Are we living inside a cosmic illusion? It's an evocative way to frame deep issues about emergence, information, and the limits of observation. But from a practical, scientific point of view, the more useful framing is: what measurable features of the universe could reveal deeper layers of structure, and how do we design experiments and build instruments to test those features? Answering that means working on multiple fronts at once, making more precise maps of the cosmos, pushing the sensitivity of quantum experiments, refining theories that relate information to geometry, and wrestling with the philosophical implications of consciousness and probability. It's a big program, and it's precisely the sort of program that can turn speculative metaphors into testable science. There's also a human story here. Our capacity to ask whether we exist in a simulated reality grows out of very tangible achievements. Computers that simulate weather, ecosystems, or neural networks, telescopes that see back in time, detectors that measure the faintest whispers of gravitational waves. The very practices that make the simulation idea thinkable are the same practices that will, if pursued, either constrain or vindicate some forms of it. In that sense, the simulation hypothesis is less an endgame than a challenge to sharpen our tools and our reasoning, none of which implies there's an easy path to a definitive answer. Some questions may remain forever beyond reach because of causal horizons, cosmic variance, or the sheer impracticality of certain measurements. Others may yield to patient, incremental work that refines our understanding of the deepest structures. That's how science has always worked. A mixture of grand speculation, careful measurement, persistent testing, and occasional revolution when an anomaly refuses to be explained away. If anything in the cosmos is going to look like a rendering artifact, it will be because someone somewhere was careful enough to listen for the faintest, most systematic deviations, and persistent enough to follow them wherever they led. If you take seriously the idea that the universe might have deeper layers, whether those layers are described by information, emergent spacetime, or the fanciful image of an external simulator, the practical way forward is the same. Translate the idea into things you can measure, then go measure them. That recipe has driven progress in physics for centuries. So let's talk about what that actually looks like in practice, what experiments and observations matter most, and how the wider cultural questions tie into the science. One of the clearest lessons of modern cosmology is that precision measurement is a powerful filter. When instruments improve by even a small amount, the space of plausible theories can shrink dramatically. That's why cosmologists are excited about incremental gains in sensitivity. Better maps of the microwave background polarization, more precise galaxy surveys, improved timing of pulsars, and more sensitive gravitational wave detectors. These instruments don't directly ask, "Are we in a simulation?" But they do ask whether the universe obeys the simple rules we expect, or whether it contains stubborn anomalies that force new thinking. If emergent space or discrete structure ideas are right, they will likely leave subtle fingerprints on one or more of these datasets. Take the microwave background again as an example. The CMB is not just an old photograph. It's a statistical map containing lots of independent modes, ripples of different sizes that carry information about the universe's early physics. If inflation happened, it left a distinctive pattern in those ripples, and future missions will push the sensitivity of polarization measurements to levels that could detect or rule out predicted signatures such as primordial gravitational waves. That detection would be a huge step. It would pin down the energy scale of inflation and narrow the class of high-energy theories compatible with the data. Narrowing candidate theories has a practical payoff. It reduces the range of possible microphysical pictures for space and time, and therefore it constrains what kinds of deeper layer scenarios are plausible. Gravitational waves are another compelling probe. We've already heard the chirps from colliding black holes and neutron stars. Those events teach us about extreme gravity in the local universe, but there's also a potential background of primordial gravitational waves that would carry direct information from the earliest moments. Detecting that background would be like getting an audio recording of the Big Bang. It could tell us about the dynamics of inflation or about phase transitions in the early universe, and that would feed back into models of fundamental physics. Any theory that claims spacetime is emergent must reproduce the same gravitational wave signatures or give an alternative that fits the data. That is how speculative ideas get disciplined by experiment. High-energy astrophysical signals play a special role in searching for subtle discreteness. Some proposals predict that very high-energy photons would travel slightly differently than low-energy ones if space has a discrete structure. By timing fast, bright events from across the universe, gamma-ray bursts, fast radio bursts, pulsar flares, astronomers can search for tiny energy-dependent delays. So far, those searches have placed very tight limits on many simple models of discreteness. No convincing dispersion has been found at levels that would indicate a coarse grid. Each null result is informative. It tells theorists which options remain viable and pushes any putative discreteness scale to ever smaller sizes. Particle physics also feeds into the conversation. Tests of foundational symmetries like Lorentz invariance, roughly, the statement that the laws of physics look the same to all observers moving at constant velocity, are extraordinarily precise. If space were discretized in a simple way, you'd expect symmetry violations at some scale, and those would show up in particle propagation or clock comparisons. The absence of observed violations constrains certain classes of models. At the same time, particle physics anomalies, unexpected decays, unexplained mass scales, or new forces could point toward new microphysics that changes how we think about space and information. If such anomalies arise and are confirmed, they become focal points for theorists trying to build coherent pictures that incorporate both the new data and the broader cosmological context. All of this is technical work, but it connects to bigger philosophical and cultural questions, because the simulation idea is not only about physics. It's also about probability, consciousness, and ethics. One of the reasons people find Nick Bostrom's argument persuasive is that it takes a concrete conditional structure. If advanced civilizations can make many ancestor simulations, then it's probable we're in one, and turns it into a statistical claim. The key words there are if and can. Whether those antecedents are true depends on unknowns about technological feasibility and on value judgments about what future beings would choose to do. That's where thinking about our own trajectory helps. Right now, we're getting better at building simulations of weather systems, of cellular dynamics, of simplified neural networks. We're also confronting ethical questions about the treatment of artificial agents. If in a few decades we start to create highly detailed simulations that contain agents plausibly deserving of moral consideration, debates about whether to run, limit, or ban certain kinds of simulations will intensify. Those debates are not abstract. They will actually shape which kinds of simulations future civilizations are likely to run. If we imagine a future where ethics strongly constrains ancestor simulations, that weakens one of Bostrom's assumptions. On the flip side, if future societies find ways to render conscious agents cheaply and treat them as morally permissible creations, the number of simulations could be huge. Without data about future values and technologies, the counting argument remains speculative. The question of whether consciousness is substrate-independent is central to that ethical and probabilistic calculus. If minds can arise from patterns of information processing and organization, regardless of the underlying material, then the prospect of generating many conscious simulations becomes more plausible. If instead consciousness requires specific biological details or quantum processes not reproducible in a computation, then simulations might be plentiful but non-conscious, or conscious instances might be rare. Neuroscience and cognitive science are gradually narrowing what counts as a plausible mechanism for consciousness, but we are far from consensus. That uncertainty is why the simulation hypothesis has philosophical legs, but not yet a decisive empirical case. There's also a practical ethical conversation already happening around AI. Imagine a near future where complex simulated agents with rich internal states can be created. If those agents can suffer, then the moral cost of running large numbers of simulations becomes real. Legislators, ethicists, and technologists are beginning to consider regulations and norms for artificial systems. Who gets rights, how to prevent unnecessary suffering, whether we should limit certain types of research. The outcome of those debates would alter the landscape for any civilization contemplating mass ancestor simulations. In other words, the social choices of the future matter for the a priori probabilities in philosophical arguments about whether we're likely to be simulated. Let's bring the focus back to the practical science again. How do we prioritize research to get the most informative constraints on these grand questions? The answer is familiar. Invest in diversified measurement programs that attack the problem from multiple angles. That means improving cosmological surveys that map structure across time, advancing CMB polarization measurements to hunt for inflationary gravitational waves, expanding gravitational wave astronomy to new frequency bands, and pushing particle physics to probe new symmetry tests and high-energy behaviors. It also means supporting theoretical work on quantum gravity, on the relationship between entanglement and spacetime, and on how information-theoretic principles could produce emergent geometry. These lines of inquiry complement one another. Observations constrain theory. Theory suggests where anomalies might show up. Anomalies drive the design of new experiments. An important intellectual discipline in all of this is careful skepticism. New measurements produce data that can be noisy, contaminated by instrumental systematics, or misinterpreted. The scientific method shines here. Unusual signals are subjected to intense scrutiny, independent checks, and attempts at replication. False alarms happen. Real discoveries are born out of anomalies that survive that skeptical gauntlet. Recall how the initial hints of accelerating expansion sparked skepticism, but after independent teams and additional data confirmed the effect, the community embraced dark energy as a real phenomenon. If an anomalous signature suggestive of a discrete substrate or information-based origin of spacetime ever appears, it will go through the same rigorous review. Alongside skepticism, it's worth keeping a pluralistic mindset. There are many plausible ways the universe could be deeper than our current best models suggest. Space might be emergent from quantum entanglement patterns. Gravity might be a statistical behavior of microscopic degrees of freedom. The cosmological constant might be set by dynamics we don't yet understand. Each of these approaches is a scientific research program with concrete, testable implications. The simulation metaphor captures some aspects of these programs: information, encoding, efficient representation. But it also risks leading people away from the specific, technical hypotheses that are actually testable. The productive move is to translate intuitive metaphors into equations and observable consequences. That translation work is already happening in certain corners of theoretical physics. Holography, quantum error correction, and entanglement geometry programs have generated precise mathematical statements in simplified settings. Those models don't prove that our universe is a simulation, but they show how spacetime can arise from information-theoretic ingredients. They also provide a language for thinking about what to look for: deviations in correlations, specific entanglement structures, or information constraints that differ from naive continuum expectations. As quantum technologies mature, laboratory experiments might begin to probe these ideas in controlled ways, creating tabletop analogs of gravitational phenomena or testing how information spreads in many-body quantum systems. Those experiments won't prove that space is coded by a designer, but they could reveal mechanisms by which geometry and gravity emerge from microscopic rules. The interplay between laboratory and cosmic scales is one of the most exciting aspects of current research. Some effects that originate at extreme energy scales may leave tiny imprints that accumulate over cosmic distances and times. Conversely, quantum information experiments performed in the lab can reveal generic mechanisms of emergence that could plausibly operate in cosmology. This crosstalk blurs the line between cosmologists and quantum information theorists, and it's producing new insights that neither field could have achieved alone. Another practical point is that not all clues will be dramatic. Many will be incremental: tighter bounds on symmetry violations, smaller error bars on the cosmic power spectrum, refined measurements of neutrinos, or better maps of dark matter through gravitational lensing. Each incremental result nudges the space of viable theories one way or another. In aggregate, these nudges can amount to a revolution because they gradually eliminate dead ends and focus attention on the handful of models that remain consistent with ever more precise data. Let's consider an example of how a single persistent anomaly could change everything. Imagine astronomers find a pattern in the microwave background that cannot be explained by any inflationary model consistent with other data, and that pattern implies a preferred scale or direction inconsistent with Lorentz invariance. That would force theorists to invent new mechanisms, maybe a discrete structure, maybe a special topology, maybe a non-trivial initial state, and experimentalists would scramble to confirm the finding with independent instruments. If those confirmations stood, the community would treat the anomaly not as an oddity, but as a signpost toward new physics. The simulation idea might appear in some discussions as one explanatory route among many, but the immediate scientific task would be to provide a mechanism that reproduces the data and leads to further testable predictions. There's also a meta point. Some questions may remain forever out of reach because of causal or statistical limits. We live inside a single observable patch of the universe. The horizon and cosmic variance place real limits on how much we can know about the largest scales. If the multiverse exists with regions forever beyond our causal contact, direct tests of those regions may be impossible. That's an important epistemic humility. Science has boundaries imposed by physics itself. Those boundaries don't invalidate science, they shape the kinds of answers we can expect. They also help separate questions that are empirical from those that are philosophical. The simulation idea straddles both domains. Parts of it could, in principle, be cut down by experiments. Other parts will remain in the domain of interpretation. So where does that leave the person watching a documentary or reading an article about simulations and cosmic edges? A useful practical attitude is curiosity tempered by a demand for empirical linkage. Be fascinated by the metaphors and the possibilities, but ask, what does this idea predict that would be different from standard physics? How could we test it? Who is trying to test it? The exciting part is that the community is doing exactly that in many ways, designing instruments, refining theoretical frameworks, and thinking hard about consciousness and computation. There are also cultural and personal responses to consider. For many people, the idea that reality might be emergent, or that we might one day be able to simulate minds raises ethical and existential questions. Those are entirely valid topics for reflection. Whether or not science ever settles the deeper metaphysical question, the technology we build and the laws we discover will have real impacts on how we live. That gives extra urgency to the ethical debates about AI and simulation design happening right now. The decisions we make today about how to treat complex artificial systems influence which future paths are open to us. At the same time, it's helpful to remember the continuity. Scientific progress brings both answers and new questions. When Newton explained celestial mechanics and Maxwell unified electricity and magnetism, those breakthroughs opened fresh mysteries about the nature of matter and the quantum world. Today's frontiers, quantum gravity, the cosmological constant, the microscopic basis of space, are ripe with puzzles that will feed research agendas for decades. Whether the eventual breakthroughs resemble emergent space models, new symmetry principles, or something else entirely, the process will be the same. Propose models, derive predictions, measure, and revise. If you want to keep an eye on where the most consequential discoveries are likely to come from in the next decades, watch these areas: CMB polarization experiments and the hunt for primordial gravitational waves, large-scale structure surveys and 21cm cosmology that map hydrogen across cosmic time, gravitational wave detectors extending to new frequency ranges and potentially sensitive to early universe backgrounds, precision tests of symmetries in particle physics and atomic clock experiments, and advances in quantum information experiments that probe entanglement, decoherence, and many-body dynamics. These are the places where theory and experiment meet and where small anomalies could grow into paradigm shifts. Finally, on the human side of the story, the very fact that we can entertain questions like, "Are we in a simulation?" is a testimony to what we've learned and built. Our ability to simulate complex phenomena, to measure cosmic photons that left the universe when it was a few 100,000 years old, and to crunch massive datasets all reflect a culture of technological and intellectual progress. The simulation idea sits at the intersection of that progress and our perennial curiosity about origins and meaning. It's a provocative thought experiment, and at its best, a spur to sharpen questions and methods. The scientific path forward is not to chase metaphors, but to translate them into concrete hypotheses and then test them. That's how we turn wonder into knowledge. In the end, the story of cosmology and the simulation debate is not a binary. Either the cosmos is a brute physical reality or it's a crafted illusion. It's a spectrum of possibilities where metaphors, mathematics, experiments, and ethics combine to produce incremental knowledge. Some strands will tighten and collapse, others will open new vistas. And along the way, we'll learn more about the structure of space and time, about what consciousness might be, and about how information behaves in the most extreme conditions. Those are discoveries with practical consequences, not just philosophical ones. So keep watching the data, encourage careful thinking, and be ready to be surprised. Science advances by converting speculative fairy tales into disciplined models that make predictions, some of which get confirmed, and some of which force us back to the drawing board. Whether the deeper layers of reality turn out to be emergent geometry, a mathematical code, or something as unexpected as we can't yet imagine, the process of discovery will be the same. Propose boldly, measure relentlessly, and let the universe answer in its own time.